Welcome everybody to the 6th week of discrete mathematics. So we will start this week with introduction to graph theory, which is one of the very important ways of modeling problems. So we start with, till now we have looked at proof techniques, we have looked at how to solve a problem like A implies B, and we have gone through a number of proof techniques, right? We have not yet gone through the proof technique of existential proof. We'll possibly take a look at them later on. But we have till now gone through constructive proof, proof by contradiction, proof by contrapositive, induction, counterexample, and so on. Now let's ask a very important question. How to solve the problem? First of all, problems come in an infinite collection of varieties. So it's not very clear whether two problems are same or not, or have they any similarity in them. All of them are unique. So there is as such no particular thumb rule about how to solve a problem. But it so happens that many problems have some common themes. And sometimes they can be modeled, or rather the problem can be phrased as a problem of some abstract object using some abstract language. Now the advantage of doing so is that one can try to attack the problems or using the abstract language. For example, we have seen that in your high school how we can solve various problems in geometry, or how various problems can be phrased in trigonometry or calculus or number theory or set theory and so on. So different problems can be phrased as a problem in these abstract objects. Now, if a particular abstract object occurs regularly to our problem then we would like to study this object separately. For example, if you remember in the case of geometry, we started studying things about circles and lines and angles because they were arising in real life quite a lot of times. Similarly, we realize that many problems in geometry or otherwise can be written as the ratio of the hypotenuse versus the sides of the triangle, which in fact gives us sine, tan and cos. And then we start studying trigonometry. So these are abstract languages, trigonometry, geometry and so on. And by studying them, we possibly come up with a unifying theory of attacking the problems. So once we have a particular abstract object appearing quite regularly, we start studying it separately. This gives rise to a new subject. And in that case, once you get a problem, we would like to phrase it or convert it to the language of the abstract object or the abstract language so that we can apply the well-known theorems. Right? So if you can convert a problem in geometry, we can apply theorems like Pythagoras theorem. We don't have to prove it again because we know those theorems. So this is the advantage of understanding or converting these problems into abstract language. Sometimes also writing the problems in a different language can help in understanding or visualizing the problem better. So let's start with 3 problems, and that will motivate us to study a particular subject. So the first problem is, So in a room there are two N people. Some of the people shake hands with each other, but in such a way that if person A and B shake hands and person B and C shake hands, then person A and C does not shake hands. Question is that what is the maximum number of handshakes possible in this case? Right? Let me quickly ask, how many handshakes can be possible when there are two N people? When I don't have the condition of this condition. So I have two N people. How many possible handshakes can there be? Let me leave it as a problem and move on to the next problem that comes up. The next problem is known as the tournament problem. So in a football league, there are N teams. Every two teams have played against each other and there is no draw. So either when team A plays with team B, either A has defeated B or B has defeated A. Proves that it is possible to number the teams in such a way that the first team will defeat the second team will defeat the third team defeats the fourth team, and so on and so forth. The N minus 1 team defeats the Nth team. Right? So this is one more problem. It is a problem like the other problem, on a real life problem. But how do we solve this problem? Let's look at one more problem. This is called the Ramsey number. So we say that for a number P and Q, natural number, with the Ramsey number RPQ is the smallest integer n, so that among any n people there exists P of them who know each other, or there exists Q of them who don't know each other. So what does the statement say? It says that, say if RPQ is equals to 100, it means that give me any 100 people, there will be either P of them who know each other, or Q of the people who don't know each other. Now I would like to understand how big this number RPQ can be. Can it be 100 or so on? And it says this following thing. Prove that RP plus 1, Q plus 1 is less than RP, Q plus 1 plus RP plus 1, Q. And RPQ is less than P plus Q minus 2, choose P minus 1. This is basically P plus Q minus 2, choose P minus 1. If you recall, this particular problem was done as a part of the induction problem. But how do we get this recurrence is the main question in this problem. So in the induction problem, we told that if we have this recurrence and we have these base cases, can we prove this statement? But I am asking the question here is that how do you prove this particular statement or this particular recurrence? Right? So here are three problems that we have seen just now. Let me quickly flash all these three problems once again. We have this handshake problem where we say that there are two N people and there are no three people who have shaken hands with each other. Then what is the maximum number of handshakes possible? Second problem, in a football tournament, we have to prove that I can order the team so that team 1 defeats team 2, team 2 defeats team 3, and so on. And the Ramsey problem, which says that what is the smallest number n such that there must be a cube of the people in any room of size with n people, there must be q of them who know each other, or there exists q of them who don't know each other. Now, what is common among these problems? First thing to note is that all the problems deals with binary relation. The first problem deals with two people shaking hand with each other. The second problem deals with team A defeating team B or team B defeating team A. And the third problem deals with whether two people know each other or not. So these are binary relations, right? Given two people, what is the relation between them? And they can be ordered for that matter. So binary relations is a very important abstract model that helps us to model many of our problems. We will see many examples of this in the next 1 or 2 weeks. And the subject that helps us study this binary relation is what we call as graph theory. This is what we will be studying. Now, graph theory, to start with, we have to define what a graph is. A graph is a particular representation of the binary relation. Okay? So, to define the relations among these elements, we usually will call the set of vertices, which are the set of elements. So, let's V1 to Vn to the set of elements. The relations that we are talking about are relations on the pairs of vertices. So these are called edges. So the sets of pairs of vertices. Okay. So in other words, if I usually denote it as E is equal to E1 to En, but Ek is of the form some Vi, Vj, which means that, so this means that Vi and Vj are related. Right? So if someone gives you the set of vertices and the set of edges, then that gives us the graph that we told of, which is called G equals to V, E. So this graph is nothing but a set of vertices and a set of binary relations. So E is a subset of V cross V. Now, this set of relations, we can use these relations to define lots and lots of things. These relations can be either reflexive or not. Right? Or in other words, Vi, Vj can be different from Vj, Vi. Correct? So depending on what restrictions or what properties we put on them, on this relation, we would get different kind of graphs. So these are all notation stuff. The way we visualize this set graphs is by drawing the vertices as blobs. Okay? But we'll come to that. But first of all, in the basic definition, let G be a graph. If I have an edge UV, and if it is a reflexive relation, that is U, V is in edge, implies V, U is in the edge, we call it as an undirected graph. Else we call it as directed graph. And sometimes, for some purpose, we can convert this whole problem into various different kinds of, we can make this abstract data structure much more complicated, and in particular we can put the weights can be assigned to each edge, and in that case we can have a weighted graph. So if G is a graph, and if there is an edge between U to V, then we say that V is a neighbor of U. That's another definition that is there. And for any undirected graph, the total degree of U such that total number of pairs UV that are there is known as the degree of V. Or this is the number of elements or number of vertices that has an edge to V. So as I told you, we usually represent this graph as blobs. So like this, A, B, C, D, E, F, G are vertices in a graph. Now the edges are usually drawn by lines. So if I draw lines like this basically says that A comma B is an edge. Also this one basically means that A comma B is an edge, and so on and so forth. So the edges are usually represented using the lines drawn between the blobs or the vertices. Now as you can see here, D is called a neighbor of A because there is an edge from A to D. Also the other thing is that since A has two vertices, so degree of A is which we call as is 2. So degree of A is 2 because it has two neighbors. Right? So this is what we call an undirected graph. When we have undirected graph, that means I don't care whether A comma B or B comma A is in the edge. In that case, there is no ordering between A and B. So we usually in that case draw it with this kind of stuff, just a straight line between the two vertices that are related. Now if the two vertices are not, if the relationship is not reflexive, that is A and B need not, A is related to B doesn't imply B is related to A, in that case we have to design a different way of writing it. We will come up with different representation. Also sometimes this relationship can have a weight associated with it. For example, think of A, B, C, D here as some cities, and then A to D is a line, meaning there is a flight from A to D, and I want to represent the time taken by the flight. In that case, we would like to put some value on the edges which denote the flight time. So in that case, we will get something like this. We have the weights, we put weights on the edges, and then we get a weighted undirected graph. This weight can represent whatever we want it to represent. We will see various examples of this. Also, if we don't want to have an undirected graph, or in other sense the binary relation is not reflexive, we usually denote the non-reflexive edges using the arrows. So this arrow means that D is related to A because there is an edge from A to D to A. But since there is no edge from A to D, it means that A is not related to D. You can think of it as one-way paths. So if these are cities, so this says that there is a flight from D to A, but there is no flight from A to D. So that is represented using this kind of a graph, and we call it as a weighted directed graph. Of course, if you don't have the weights, we just call it as a directed graph. Now graphs are, you must have seen graphs in various places. Now you must have seen graphs in various places, and they are a very useful way of representing data, and it also helps us to formulate problems in a nice way. Before we move on, let's ask a quick question. How many edges can there be in a simple undirected graph on n vertices? Okay, so let's see. So the first vertex, so if I have say n vertices, the first vertex can have edges to all of them, right? Which is n minus 1. Plus, second vertex now already has edge to the first one, can have edge to the second and all of them, which is n minus 2. Third one can have edge to everything on its right, which is n minus 3. And you keep on adding till this vertex, which has edge to 1. So just 1. So this is actually equals to n into n minus 1 by 2. The other way of looking at it is that between any two vertices, I can draw an edge. So the total number of edges that can be there is number of ways I can choose two vertices from this n vertex, which is n choose 2, which is of course equal to this also. So the total number of edges that can be there in an undirected graph for n vertices is n choose 2 or n into n minus 1 by 2. Now graphs are a nice way of expressing relationship between objects, particularly binary relationship. They are very simple, yet they are very general, in the sense that they are simple to understand what they are, and yet they are used to represent quite a number of complicated relationships and problems. There are various examples of graphs that can be there, but I have pulled out a few of them. Here is one. Say this is called the friendship graph. So where every person is a vertex, and we say that if two persons are friends, then there is an edge between the respective vertices. This is used a lot for understanding things like social networks like Facebook. So all the users are vertices. Between any two vertex, I draw an edge if they are friends in Facebook. Question is that how well connected they are and so on. So here is an example of a friendship graph. Typical friendship graph from one of the. So I have this points with every vertices. So this is one vertex, this is one vertex, this is one vertex, and so on. So all the vertex represent people, and there is an edge if they are friends with each other in the social network. This helps us to understand whether there is a various structures on the friendship graph. For example, as you can see in this particular friendship graph, one can see this one and say that, okay, this set, maybe this set of people are the ones who are in a particular country, this set of people are there in another country, and so is this set of people in another country. So this is called clustering problem, or understanding the friendship graph to understand some structure on the graphs, or structure of the network. Another example is the internet graph. This is used a lot for Google to crawl, where every website is a vertex, and if a website has a link to another website, then there is a direct edge from the first vertex to the second vertex. This is, of course, gives us a directed graph, and this is used for web crawls of Google. When you search something on Google, Google uses this one. So these are examples of real life problems or real life data that is represented in graphs and is used a lot in our modern day technologies. So this is the internet graph. I think it came out a few years ago. This is the representation of the internet graph. Now, another very use of this graph are of course road networks, where we have vertices are cities and edges are roads. And in fact, we can also have numbers assigned to them, which basically indicate the number of the distance between them. So for example, here it says that Brussels to Paris is distance 290 kilometers. So maybe this is a road network that is there. If you ever open a map, you will see such structure like this. So graphs are also used for designing road networks, railway networks, and so on. There are many other problems in real life that can be designed as problems in graph theory. Thus, studying the structures of graphs and designing algorithms for graph problems is an important field. So studying the structure is what we will be focusing on this particular subject, in this particular course. Now this was all introduction to graphs. How does it help solve our problems? So let's see, here is the problem that we have, right? The first problem, there was in a room there are 2n people. Some of the people shake hands with each other in such a way that A and B shake hands. If A and B shake hands and B and C shake hands, then A and C does not shake hands. What is the maximum number of handshakes possible? Now, can we model this problem using graphs? It's not very hard to see what is going on. First of all, let there be 2n vertices. So every vertex represents a person. So there are 2n vertices, V1 to V2n. And if two persons shake hands with each other, we draw an edge. So there is an edge between Vi and Vj if Vi and Vj shook hands. Now if Vi shakes hands with Vj, then Vj must shake hands with Vi. So in other words, this relationship is reflexive, and which means that the graph is undirected. Now what is it we are saying about this condition that if AB shakes hands, BC shakes hands, then AC cannot shake hands? So if I see something like that, it's a vertex, this is a vertex, they shake hands, and this shake hands, then I cannot have a shaking hand here. Which in other words means that there is no triangle. We can call this one as a triangle, right? So there is no triangle. And now we are asking how many handshakes can there be? So in other words, we are asking that how many edges can there be? So the problem reduces to a nice problem in graph theory, which says that a graph on 2n vertices without a triangle, how many edges can there be? So we have converted this problem into a nice problem in graph theory. Quick observation, if the condition was that there was no triangles was not there, then how many edges can there be? It was all the possible edges that can there be in a graph, right? Which is, of course, n choose 2. We just now saw some time ago. So this is n choose 2. But now we have been given the condition that there cannot be any triangle. So can we guess now how many edges can there be when there is no triangle? Can you give me a bound? Of course, n choose 2 is an upper bound. But what about something less than that? Can you come up with some example? Can you come up with a lower bound? Or in other words, can we create a graph which doesn't have a triangle and yet has quite a number of edges? So here is one hint. If I have n vertices in this vertex, in this part, n vertices here, and the edges are all going from left to right. Okay, so these are the edges. This is something called a bipartite graph, meaning it's a graph where I have split the vertices into two parts. Let's name them. So usually they are named as left and right. Each of them has n vertices each, and the edge set can be the complete set, or it can be a subset of the complete set between L and R. So between any two vertex, I can draw an edge. Any two vertex, one from left, one from right. Note that this particular graph cannot have a triangle, will not have a triangle, right? Well, if we had a triangle, it would have been triangle something of this form, right? Something going like this, and a side triangle like this. But then I have not drawn a single edge between two vertices in L. So that cannot be possible. Right? So this L cannot have a triangle. And how many edges are there in this graph? There are n vertices here, n vertices here. All the pairs can be there. So the size of the edge can be n square. So here is a graph which does not have a triangle but has n square number of edges. So in the answer to the question that was asked, how many edges can there be in a graph on 2n vertices without any triangle, we have got a lower bound which is n square. There can be n square. Now it so turns out that n square is in fact the right answer, but can we prove that thing is the question. How do we prove that a graph on 2n vertices without a triangle can have at most n square edges, and that is tight. Right? So the guess would be n square. That is the maximum number of edges in a graph on 2n vertices with no triangle is n square. Can we prove that? And that is what we will be doing in the next class. In the next video lecture, we will solve this problem, and also we will see how to represent other problems using graph theory.